Hello everyone and welcome to today's webinar in the SERDP and ESTCP webinar series. My name is Jennifer Nyman and I am a Senior Engineer at Geosyntec Consultants in Oakland, California, and the coordinator of today's webinar series on behalf of SERDP and ESTCP. I will be facilitating today's call. The webinar will consist of a brief overview of SERDP and ESTCP by Dr. Andrea Leeson, followed by a list of upcoming webinars in the series. After Andrea's opening remarks, we will transition to the technical portion of the webinar. Today's event features two presentations on long-term monitoring issues at chlorinated solvent sites. First, Dr. Ron Falta from Clemson University will present an approach developed with ESTCP funding to model matrix diffusion effects in low permeability zones at chlorinated solvent sites. Ron's presentation will be followed by a brief question and answer session. Then Poonam Kulkarni and Dr. Tom McHugh will provide a joint presentation regarding minimizing and managing variability of long-term groundwater monitoring results, followed by a second question and answer session. We will conclude the webinar with an interactive Q&A session with all three speakers. Today's broadcast will be listen only. You may submit questions by using the chat box on the left-hand portion of your screen. You do not need to wait until the Q&A period to submit your questions. In fact, we encourage you to submit questions in advance of that session. On this slide, we have provided a few suggestions in the event that you experience any difficulties with the broadcast audio. Typically, any delay will be fixed if you refresh your screen or call into the conference line. However, if you continue to have problems, please submit a comment using the chat box in the lower left corner of your screen. With that, I would like to introduce Dr. Andrea Leeson, who is the Deputy Director of SERDP and ESTCP, as well as the Program Manager for Environmental Restoration. Andrea has been with SERDP and ESTCP since 2001. Previously, she was a research scientist at Battelle Memorial Institute, where she conducted research on in situ bioremediation. Andrea?
Thank you, Jennifer, and welcome everyone to SERDP and ESTCP's webinar. SERDP is the Strategic Environmental Research and Development Program established in 1991 by Congress as a partnership between the DoD, the Department of Energy, and the EPA. SERDP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. SERDP funds both fundamental research as well as advanced technology development that ultimately impacts real-world environmental management. ESTCP is the Environmental Security Technology Certification Program in which we demonstrate innovative environmental and energy technologies. These investments capitalize on past investments under SERDP or other research programs and are designed to transition technology out of the lab and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory guidance. SERDP and ESTCP are complementary programs with much of SERDP research occurring at the lab and pilot scale with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally supporting lab efforts are conducted. There are 4 program areas in SERDP, 5 in ESTCP. The Energy and Water program area is only in ESTCP, while the other 4, Environmental Restoration, Munitions Response, Resource Conservation and Climate Change, and Weapons Systems and Platforms are SERDP and ESTCP programs managed jointly by a designated program manager. Our webinar today is focusing on research and demonstrations that were conducted under the Environmental Restoration program area. Environmental restoration has essentially 5 main areas of research: contaminated groundwater, contaminants on DoD testing and training ranges, contaminated sediments, wastewater treatment, and risk assessment. Our webinar series will be highlighting research and demonstration efforts from each of the 5 program areas. As you can see, our webinars will cover a broad range of topics with upcoming topics covering microgrid technologies in sensitive munitions, geophysics, and water conservation. Our next topic under the Environmental Restoration Program area will be on June 2nd and will cover recent research on insensitive munitions. You can find more information about upcoming webinars at this link shown on the slide. Registration is now live for all webinars listed through June 30th. I hope you enjoy the webinar today. Jennifer?
Thanks, Andrea. And now it's my pleasure to introduce Dr. Ron Falta. Dr. Falta is a professor of environmental engineering and earth sciences at Clemson University in South Carolina. He has served as the PI on multiple research and development grants that have focused on subsurface remediation and model development for chlorinated solvent sites. Dr. Falta developed the US EPA REMChlor transport and remediation model. He has authored more than 60 research papers and book chapters in these and related areas. Ron?
Thanks. Well, today I want to talk about some work that we're doing to develop a useful approach for modeling matrix diffusion effects in low permeability zones. The agenda for the talk today, I'll introduce the problem and issues related to matrix diffusion and talk kind of briefly about current modeling approaches. And then I want to primarily focus on a new method that we're developing, a high-resolution semi-analytical kind of hybrid method that we're going to use in a new program we're developing called REMChlor-MD. And then I want to show some examples of how we're testing that new methodology with known solutions for matrix diffusion in Aquitards and in fractured rocks. So the overall objective and expected benefits of this work are to develop a new kind of a groundwater source plume remediation screening model that's going to be called REMChlor-MD. And the key aspect of that is that it considers matrix diffusion in the plume. And the idea is that this should allow site managers and other stakeholders to quickly assess the likely impacts of source and plume remediation, including natural attenuation of either the source or the plume. And it's hoped that that would improve the decision-making process and help eventually reduce costs and ensure the effective use of limited resources in the site remediation process. So this is kind of a standard picture of a DNAPL site from perhaps an industrial facility where we might have chlorinated solvent at the DNAPL that's migrated down past the water table, has accumulated on the clay layer, and we have groundwater flowing through that contamination, and so we get a plume which may be several miles in length or kilometers. So we've had a tremendous effort over the past 30 years in looking at how to remediate the source zone and how to remediate the plume, but something that perhaps wasn't appreciated until fairly recently is the secondary effect that can happen from diffusion from the plume and from the source into low permeability layers. And in this case, this figure is showing diffusion into an underlying clay Aquitard. Well, the issue with that is that over time, as these contaminants diffuse into these low permeability zones, they build up a reservoir of mass in those zones. And if you then go and remediate the high permeability zones, which are more accessible, the back diffusion process caused by the reverse concentration gradient can recontaminate the aquifer. And this really becomes an issue when you have a many orders of magnitude concentration that you have to, reduction that you have to achieve. For example, with the chlorinated solvents, the sources are 4 or 5 orders of magnitude higher in concentration than regulatory standards. So this back diffusion process, I don't think anybody really knows how long it would last, but simulations suggest many decades to centuries and available data. So when you think about matrix diffusion, there are different settings in which it could occur. Perhaps the simplest one would be an aquifer Aquitard system where there's diffusion along the base of the aquifer. But certainly in real systems, we have layered systems with high and low permeability zones. And in those kinds of systems, you'd expect matrix diffusion to be stronger or have a larger influence because of the larger surface area available for diffusion. A more realistic system would be a general heterogeneous system with lenticular low permeability features, although that would behave in a lot of ways similarly to the layered system. And then probably the worst case scenario as far as matrix diffusion would be a fractured porous media, like a fractured sandstone, where you have fairly high rates of fluid flow through the fractures, but very small volumes in the fractures, and then very large interfacial areas with the unfractured matrix for the diffusion effects to take place. And so trying to model these effects with conventional numerical models turns out to be pretty difficult. It can be done, but it's not straightforward. So there have been some good examples of simulations of matrix diffusion, and these three pictures show a few cases. The first picture here is a pretty famous experiment done by Leanne Donner and Tom Sale. It was a sand tank with clay layers, and they flushed fluorescein dye through it and then looked at the back diffusion. And Steve Chapman and others did some high-resolution simulations of that in 2 dimensions and were able to almost exactly reproduce those results. Similarly, Beth Parker and others did high-resolution simulations of the Aquifer Aquitard system and achieved good comparisons with field data. And then Chapman and Parker have done studies of detailed numerical modeling of a fractured network with contaminants moving through the fractures and diffusing into the matrix. So these kinds of simulations have been done, but they required very, very fine grids and very high resolution, and they were only done in 2 dimensions. So it seems likely that that kind of high resolution approach, while it's very useful for research, maybe is not that practical for the typical 3-dimensional field scale simulation. And the reason for that would be that the matrix diffusion process is controlled by the concentration gradients right at the interfaces, and those gradients vary at the millimeter to centimeter scale, particularly when the concentration changes quickly. Yet when we try to model a field scale problem, our grid blocks are at least tens of centimeters and maybe several meters in dimensions. So what that means is that these key matrix diffusion processes happen at a scale that's smaller than our grid blocks. So our only easy way to model that is to make the grid blocks smaller, as is shown in the figure here. These are from Chapman's paper, where modeling the Donner experiment. Those are the size of the grid blocks that they use to reproduce that experiment. So we're trying to develop an alternative approach that moves away from that a little bit. And this new approach is going to be called REMChlor-MD, as I said, and this is going to be intended as a screening level source plume remediation model that's based on the current REMChlor framework. If you're familiar at all with REMChlor, that's the EPA program that was developed with SERDP funding that simulates source and plume remediation, but kind of in a simplistic way. So the idea with this kind of a model, like REMChlor, is to have a simple flow field, also like BioChlor. The flow of groundwater is just going in one direction at a uniform velocity, but to include the important processes of advection, dispersion, retardation, first-order decay with daughter products, and then to allow source and plume remediation that are independent of each other and that can occur at different times in different locations. So those kind of capabilities are already in the REMChlor, but the difference then with this new version that I'm going to talk about is that we would add the matrix diffusion process in the plume. And so what I wanted to spend the rest of this time talking about is this new method that we're using to model matrix diffusion in the plume, the semi-analytical method. So the basis of this method actually comes from petroleum engineering. There was an elegant method developed in 1980 by 2 Canadian petroleum engineers for heat conduction. And the problem they were looking at was thermally enhanced oil recovery in a thin oil reservoir that was bounded by impermeable cap rocks, and a lot of heat is lost by thermal conduction into the cap rocks. So back in 1980, of course, they didn't have fast computers, so they didn't want to have to do a fine grid simulation of the cap rock, and they came up with this way where they could only have to model the reservoir and then treat the thermal conduction into the cap rock with this semi-analytical method. So the way this works is that they're only modeling this transmissive zone, which in their case is the oil reservoir, and then they treat the exchange of heat in the low permeability confining layer by representing the temperature there with what they call the trial function. This is just a function that's assumed to approximately fit the vertical temperature profile from the interface vertically downward. So this temperature trial function, the first term in that function is the temperature in the reservoir itself at the interface. And then the second term is an adjustable parameter P times the depth into the confining layer. The third term is adjustable parameter Q times the depth squared into the confining layer. And it's all multiplied by a negative exponential that also depends on the depth into the confining layer. So the whole trick to this method then is figuring out what the P and the Q should be. Those are algebraic expressions, and they're arrived at by forcing that trial function to satisfy the differential equation for heat conduction. So once you have those equations, those parameters are updated at each numerical time step, and that trial function is differentiated to figure out the heat flux into and out of the confining layer. So it turns out that that process is almost a perfect analogy for the problem that we want to do. So for the heat conduction problem, you have an oil reservoir that's hot, and it's exchanging heat with a cap rock through thermal conduction. For our problem, we have an aquifer with a dissolved chemical, and it's exchanging mass with an Aquitard through matrix diffusion. But the mathematics of those two processes are almost identical. The differential equations are almost the same, with really the only significant difference being that there's a decay term in the chemical diffusion equation. And of course the parameters are different, but structurally they're the same mathematics. So that suggested to us that this procedure might work. So to implement this for matrix diffusion for the case of an aquifer and Aquitard, we would build a numerical model just of the aquifer. So that's the only part we would discretize. And then we would allow the interaction with the Aquitard to be done with a trial function that is similar to that temperature one that the petroleum engineers used. But now instead of temperature, we have concentration. And instead of the temperature at the interface, we have the concentration at the interface. So that concentration would be the concentration in these grid blocks that are touching the Aquitard. So the trial function, though, has the same structure, the same features, and it has the two adjustable parameters, the P and the Q. And the D in that exponential is just a time-dependent diffusion distance. It varies with the square root of time. And again, that's similar to the heat transfer method. So as I said, the real trick to getting this method to work, though, is figuring out the algebraic expressions for P and Q. And the way you do that is you plug in that trial function into the differential equation for diffusion and force that differential equation to be obeyed exactly at the interface between the high and low permeability. And then you also force the equation to allow for the mass conservation in the low permeability zone. So you want the mass that's diffused in the low permeability zone to be consistent with the mass that's diffused across the interface and that's decayed. So the exact form of the P and the Q depend on the geometry of diffusion. For example, an infinite Aquitard is different than parallel fractures. And it also depends on the chemical reactions, whether you have parent-daughter reactions or not. So for the rest of this talk, I want to show some examples where I'm comparing this new methodology with known solutions, so exact solutions for matrix diffusion. And the simplest case that I could think of is one where you have an aquifer and an aquitard, but you just represent the aquifer with a single grid block. So this is a numerical simulation with only one grid block, but it's going to model transient diffusion into and out of the aquitard, and that's being modeled again with this semi-analytical approach with the trial function. And the nice thing about this problem is that there's an exact analytical solution available for this, for transient diffusion with first-order decay. So the scenario here is that at time 0, the concentration in the aquifer is suddenly raised to 100 milligrams per liter of TCE, and it's maintained at that concentration for 50 years, and then it's suddenly reduced to 0. And we just follow the diffusion process out for 100 years using this method. So these are the results of the simulation. The left-hand side here is showing the concentration profiles in the clay as a function of time. So the vertical axis is the TC concentration. The horizontal axis is the depth into the aquitard. And I'm showing 4 different times here. So the blue line, the blue symbols are showing the concentration profile in the aquitard at 10 years. And then the red line or symbols are showing it at 50 years. And in this simulation, the solute or the TCE was decaying in the aquitard. So eventually you reach a point where the diffusion into the aquitard is balanced by the rate of decay in the aquitard. Then at 50 years, the concentration is reversed, and I'm showing a period 10 years after that, so 60 years here. So this is the back diffusion period, and then this is at 100 years, and pretty much everything's gone. But the semi-analytical solution here is shown with the symbols, and the exact solution is shown with the solid line, and they are in close agreement there. The plot on the right-hand side shows the accumulated mass in the aquitard as a function of time. So it increases quickly at first and then flattens out due to the fact that the TC is decaying in the aquitard. And then at 50 years, the aquifer suddenly reduced the concentration to 0, so then the mass diffuses back out of the aquitard. And again, the semi-analytical solution does a good job of matching the exact solution here. And I should point out that the simulation, it's hard to measure something that runs that fast, but it was on the order of 1/100th of a second or two to do the entire simulation, because it's all analytic or semi-analytic. So a more complicated comparison would be with the 2-layer Dandy Sale solution. This is a sophisticated analytical solution that considers 2-dimensional advection, dispersion, and decay in the aquifer, and then 1-dimensional diffusion in the aquitard. And it's all completely linked together mathematically. That is a part of the ESTCP matrix diffusion toolkit that many of you might be familiar with, and this is a screenshot from that tool. So this is available and is fairly widely used. But as I say, it's a very sophisticated and complicated solution. So we did a comparison to this using a 2-dimensional cross-sectional model. The top part is the aquifer, and that's modeled using a standard numerical finite difference, but then the semi-analytical method is used for the aquitard. And with this solution, it simulates a DNAPL source at the bottom of the aquifer on the upstream side, which persists for 50 years, and then it's removed suddenly, and you have a back diffusion period. So the top graph here is showing the projected concentration in the aquifer, and this is in the bottom 10 feet of the aquifer, 10 years after the DNAPL source has been removed, and showing that concentration as a function of distance down gradient. So this is the back diffusion period, and the reason that this mass is in the aquifer is because of back diffusion. And the further down gradient you get, the more mass is diffused up out of the plume. But the two models, the exact Dandy Sale solution and the semi-analytical solution, compare pretty well. Not exactly, but closely. The bottom graph is a comparison of the concentrations in the aquitard, and here the vertical axis is the depth into the Aquitard, and the horizontal axis is the concentration. And this is at a distance of 150 meters down gradient of the source. And as in the earlier one, it's at an early time, 10 years, and then a later time, 50 years. And then the DNAPL source is removed, so that's 60 years, and then at 100 years. And while the two methods don't compare exactly, I think they're close, and in particular the gradients at the interface tend to be close. So those cases, the last two cases, were for this special case of having an Aquifer Aquitard system. And what's unique about that mathematically is that the Aquitard acts like it's almost infinite. But you can modify this approach to apply to finite embedded heterogeneities. You have to account for the volume fractions of the high and low permeability zones and the interfacial area of the two zones, and also the diffusion length. But if you do that, you can approximately represent the layered system or the heterogeneous system or even the 3D fractured system. And you can also modify this method to allow for coupled parent-daughter reactions. For example, the PC-TC-DC vinyl chloride chain reaction. So I want to show a case that is a pretty difficult one, matrix diffusion in a fractured rock. And I view that as sort of the most severe case for matrix diffusion because we have very small volumes in the fractures with very large surface areas and large matrix volumes. For this case, there is an exact analytical solution available. It's actually been available for a long time from Siddiqui and friends. This is a pretty sophisticated solution as well. It assumes one-dimensional advection, dispersion, retardation, and decay in the fracture, and then perpendicular matrix diffusion and decay. So the scenario that's modeled with Cray flush would be fractures that are parallel to each other. They're separated by distance of 2L, and that spacing can be whatever you like. So the test case I want to show you, I picked a close fracture spacing. It's only 1/10 of a meter, so that would only be a few inches. So this test case would be a highly fractured system where there really would be a lot of area for matrix diffusion to occur. At the same time, there's also a strong interference effect from the adjacent fractures because diffusion from a fracture down here upward would be met by diffusion from this upper fracture downward. So there's a boundary effect that's important to account for. This problem includes decay, and it has a high velocity, 1/10 of a meter per day. So the scenario will be we introduce the contaminant for 10,000 days, which is about 30 years, and then flush it with clean water for another 10,000 days. And if you ran this problem without matrix diffusion, the contaminant would go about 1,000 meters in that 10,000 days, and then it would be flushed out pretty quickly. But as you'll see with matrix diffusion, it's not at all like that. So these are the results of the simulation, and the left-hand graph is showing the concentration in the fracture as a function of distance along the fracture from the source. And this is the loading period. So this is the period where the contaminant's being added to the fracture. The first curve here, the blue dots in the solid line correspond to 1,000 days, and the red dots and solid line correspond to 10,000 days. So after 10,000 days, the contaminant's only gone about 100 meters, whereas without matrix diffusion, it would have gone 1,000 meters. But that's because of the tremendous rate of mass transfer out of the fracture and into the matrix because of matrix diffusion here. Then we go to the unloading period. So now the fracture is being flushed with clean water, and the yellow symbols here in the solid line correspond to 11,000 days. So that's 1,000 days after flushing started, about 3 years. And really, the fracture is not being flushed at all much except just in the first few meters. And even after 20,000 days, which is about 30 years after flushing started, there's still very high concentrations in the fracture because of matrix diffusion. So it has a very, very dominant effect in this environment. But I guess the main point would be here that the semi-analytical method that I've been describing closely matches that exact analytical solution. So that's encouraging because I view this as a difficult test case. So I want to wrap this up. We're developing a screening level model that we're going to call REMChlor-MD, and the important features of it are that it includes the source plume remediation scheme similar to REMChlor, but it also has matrix diffusion. And the goal of this is to be an easy-to-use tool that runs fast and that is easy to learn, that allows managers and stakeholders to efficiently judge the impacts or assess the impacts of proposed source and plume remediation schemes, including natural attenuation. This model will have a graphical user interface that will have a look and feel that will be kind of similar to BioChlor and especially similar to the matrix diffusion toolkit. It'll have a user's guide with test problems similar to the ones I showed. And we'll be offering web-based training, and the code will be available free. So I'd like to acknowledge my partners on this ESTCP project, Chuck Newell with GSI and Shala Farhad with GSI, and they're going to be focusing on the graphical user interface and also on the user's guide, but we're all working together on the overall structure of this. And Kara Lynch with the US EPA Region 10, who's helping with the overall design and feel of the program. So if you're interested in learning more about this, you can go to the SERDP ESTCP website, and my contact information is listed at the bottom here. So with that, I think we're at the question and answer period.
Okay, thank you, Ron, very much for a wonderful presentation. And I'd like to remind our audience at this time to submit questions using that chat box on the left-hand portion of your screen. We are receiving a couple of questions on this first presentation that Ron will answer now. The first question, Ron, is how important is back diffusion in low concentration chlorinated plumes? So for example, at concentrations less than 10 micrograms per liter.
I would say it's less important than. What you have to look at is the range in the concentration that's in the high permeability zone compared to the regulatory standard. And if it's, milligrams per liter and the regulatory standard is micrograms per liter, then matrix diffusion is likely to be a big problem. But if it's only twice the standard, then it's less likely to be a problem. So the concentration really does matter quite a lot, and it's the orders of magnitude that really matter, I think.
Okay. And when do you expect that this new model will be available?
Probably test version in about a year, and the final version a little bit after that.
Okay. And can the model handle general parameters in the transmissive domain so that it can be used in a more general transport model? So for example, could it be incorporated into a conventional transport model like MT3D?
I feel like this method definitely could be incorporated into something like MT3D. That is not something that we're doing right now, but it is something that makes a lot of sense, I think.
Okay. The next question asks about some details on the P and the Q parameters and how they are defined and estimated.
So they all come from taking that trial function and plugging it into the differential equation and forcing that differential equation to be exactly satisfied at the interface between the two media, and then also plugging that trial function into a mass balance equation that relates the rate of mass flow across the interface to the rate of mass change in the low permeability. And you wind up, after you do the calculus in algebra, with two equations and two unknowns, and then you get these closed form algebraic expressions for P and Q. They're quite lengthy, but once you get those, then you're kind of done. You just program that and then recalculate them at every time step.
Okay, thank you. What is the difference between using REMChlor-MD and using the matrix diffusion toolkit, which uses the Dandy Sale model?
Well, they will be both, of course, doing matrix diffusion, but the REMChlor-MD program will be more like a BioChlor type program where you have a source and you have a plume and you it's three-dimensional. The plume is three-dimensional. And it'll be like REMChlor in the sense that you can manipulate the source to simulate remediation at any time in the future, and you can manipulate the decay rates in the plume in space and time to simulate different bioremediation activities. So it's complementary to the matrix diffusion toolkit, but it's more of a capability like REMChlor or BioChlor.
Okay, thank you. And have you done any tests with any cases with multiple peaks in the concentration profile within the diffusion domain?
I haven't, but in the original journal paper from the Canadian petroleum engineers, they did a test case that had a kind of a sawtooth temperature profile, and they had an exact solution for that, and the temperature solution matched that pretty well. So I expect that it would work okay for that case, but I have not personally tested it.
Okay, and as a follow-up to that, one audience member was asking where they could find the references for some of these analytical equations that are being used. Have they been published anywhere, or will they be published along with REMChlor-MD?
They have all been. Well, most of them have been published. The one for transient diffusion with decay, I adapted that from a book by Crank, but I don't know if it's been published for the exact problem we're looking at, but it mathematically is available. If the person wants to send me an email, I could give them the reference.
Okay, great, thanks. Ron, the next question is about the sensitivity of the model. How sensitive is it to differences in the assumed thickness of the low permeability zone? And is there a thickness beyond which the effects are negligible?
It is sensitive to that thickness. I'm not sure what the critical thickness is. It would depend on the time scale, but I would expect it to be on the order of a half meter to a meter or so. But I haven't done the sensitivity study yet.
Okay. And we've had a couple of questions about the applicability of this model to real-world sites. And one of the questions is, can you discuss the potential limitations of this tool in settings where chemical gradients develop within a very large matrix volume?
Well, a big limitation of this tool would be that it assumes a simple one-dimensional flow field. So although it splits that flow field into a high permeability and a low permeability part, the velocity and the high permeability part is all the same. And another limitation is that it's kind of a binary system. This model has to assume that either the water flows through the zone or it doesn't. It can't have a continuous variation. And the other limitation would be trying to figure out how do we evaluate the parameters that we need for the model? What are the interfacial areas between the high and the low permeability, and what are the volume fractions, and what are the critical diffusion lengths? And that latter problem is something that we're working on in a SERDP project that's led by Bob Borden, trying to relate high-resolution direct push measurements to figuring out those parameters to put into a model like this.
Okay, thank you. And related to that, is there any benefit to collecting soil samples from the Aquitard and performing analyses on them?
Well, I think there's probably always benefit in that. Seeing the extent to which matrix diffusion has actually occurred would be a key thing there. You could also get some of the parameters that you would need for the modeling, like the porosity and fraction of organic carbon, that kind of thing. Okay.
And does this back diffusion model incorporated degradation terms such as biotic or abiotic dechlorination?
It does. It assumes that that is a first-order decay process that happens in the aqueous phase, but the parent, like PCE, can degrade to a daughter like TCE with a variable rate, variable yield coefficient. And so I'm setting it up for 4 components, and the decay rates would be independent for each of the 4 components, and the yields would be independent for each of them. And then they'll also be made spatially and time varying in the final version.
Okay. The next question is, for matrix diffusion, how deep does it typically penetrate into the low permeability zones, or what's the range of that?
It depends on, it varies with the square root of time, so it sort of slows down with time, but I think there are some data that show it going a meter in some cases, or maybe even more than a meter. If it has enough time, 50 years, it can go a ways.
Okay. And can you provide some more details about a case where there's an impacted alluvial zone that consists of just a few low permeability subzones? How would the model be applied to that case when there are multiple low permeability subzones?
Yeah, so the strategy there will actually be to use big grid blocks that include those zones inside the block, and then use this 2-domain idea to represent the exchange between the high permeability and the low permeability. So it's kind of the reverse of what you might think. Instead of trying to use a really fine approach, instead they're put inside of the big grid block, but then this semi-analytical method can resolve the exchange between the 2 media.
Okay. Thank you. And with that, we'll end this question and answer session. But Ron will come back for a general question and answer session at the end of the webinar. So if you have more questions for him, please do submit them, and there will be a chance for us to ask a couple more at the end. Thanks, Ron.
You're welcome.
And the next part of the webinar will be presented by 2 speakers. The first is Ms. Poonam Kulkarni. The second is Dr. Tom McHugh, both of GSI Environmental. Ms. Kulkarni earned a BS in Chemical Engineering from UT Austin and a graduate degree in Environmental Engineering from Rice. And she is a licensed professional engineer. She has served as the co-PI on multiple research projects, including this topic, as well as applying enhanced bioattenuation technologies at chlorinated solvent sites, and demonstrating passive soil vapor extraction technologies. After Ms. Kulkarni finishes her presentation, she will pass it to Dr. Tom McHugh. And Dr. McHugh is a toxicologist with extensive project experience in site investigation and restoration, risk assessment, data mining, and statistical analysis. He received his PhD in toxicology from the University of Washington. Dr. McHugh has developed training classes and has contributed to state and federal guidance documents, and he is a diplomat at the American Board of Toxicology. Poonam, I'll now turn it over to you.
Great. Thank you, Jennifer, and welcome everyone. We're happy to be presenting on today's webinar. Here's a quick overview of our talk this morning. First, I want to discuss why reducing short-term variability in groundwater monitoring data is an important topic to focus on. And then we'll talk about 2 approaches our team took to work on the problem. In the first approach, we compared the short-term data variability of the most commonly used sampling method, the standard low flow, to that of alternative sampling methods. And our overall goal here was to see if we could decrease short-term variability and also evaluate concentration bias and cost of implementation. And this was because of our previous SERDP study that looked at causes of variability. Here we found that variability isn't due to the labs or well construction, but it may be sampling methods and procedures. And though there's been previous work that has compared concentration results of various methods, to our knowledge, this is the only study to compare the short-term variability in such a controlled way over multiple rounds of sampling. And in the second approach, our team created a toolkit which helps to optimize monitoring frequency and analyze trends in existing data set. This approach will be discussed by my colleague, Dr. Tom McHugh, in the second half of the presentation. Now I'd like to start off by defining short-term variability. Here we have an example concentration versus time graph for a typical groundwater contaminant in a specific well where the solid line shows the long-term attenuation rate. But as you can see, there's short-term variability in the event-to-event measured concentrations, and this variability then makes it harder to evaluate that long-term trend. And if we can't determine the long-term trend accurately, then more monitoring data may be needed, and our ability to make proper site management decisions may be more limited. And of course, acquiring more monitoring data can be costly. So for example, monitoring of 40,000 wells costs more than $100 million in Department of Defense facilities across the country. Now we'll switch gears to talking about our first approach, which was a field demonstration program. What you see on the slide are the 5 different sampling methods that we compared. Method 1 is the most commonly used standard low flow method, which includes purging at low flow rates and monitoring parameters like dissolved oxygen, temperature, and pH until those values stabilize. Methods 2A and 2B we're calling the alternative low flow method. Here we purged 2 different fixed volumes, a small volume of 3 liters and a larger volume of 18 liters. And these gave us 2 different samples which were collected on the same day. Finally, methods 3 and 4 were both no purge methods, using the commercially available SNAP sampler for method 3 and the hydrosleeve for method 4. So to reiterate, our overall goal was to modify methods 2A through 4 to try to decrease short-term data variability as compared to the standard low flow. And here we show the specific modifications we made to methods 2A through 4. On the left side of the chart, what you see are the modified procedures we applied to the different sampling methods. First, as you notice, we didn't change the standard procedures of the typically used standard low flow. And the green check marks show what changes were made to each of the alternative methods as applicable. And we chose these particular alternative procedures based on other studies that have looked at their impact on data quality. So for instance, for those methods that involved a filling of a vol vial, we kept vials for analysis even if they had small bubbles of up to 2 milliliters of headspace. And this was based on a 2001 study that showed that analyzing samples with bubbles had little or no impact on concentration results. And the other idea was that when people spend a lot of time trying to get rid of bubbles by opening vials, topping off, and reclosing, you can actually lose some volatiles in the process. We then applied these methods in a field program that was conducted over the course of almost a year, and the work was done at 2 different sites, one in Texas and the other in California. And at each site, we chose 8 wells in a chlorinated solvent plume. So the chart on the slide shows the chronology of how the sampling methods were applied. Method 1 was used first, followed by methods 2A and 2B, and so on and so forth. And all 5 methods were done in this specific sequence 6 times at each well. So altogether for the 2 sites, we had a total of 480 samples. Also for each sample, multiple constituents were analyzed. And our final data set then had over 3,200 measurements, which were then further analyzed for short-term variability and concentration bias. Now before we get into the details of the short-term variability results, I wanted to briefly mention one point about concentration bias. Concentration bias refers to when a particular sampling method consistently gives higher or lower results than the average of all of the methods. And this is important because a particular method could have low variability, which would be good, but the results could be consistently higher or lower than other methods. And what we found was that there were only small differences among the concentration results from the different methods, as you can see on the x-axis of the graph. And this is also consistent with other studies that have looked at this topic. Here we show the results of the variability analysis, which used pairwise measurements to evaluate the concentration differences. The first graph on the left shows the median short-term variability, while the graph on the right shows the 90th percentile short-term variability for all 5 methods. And the main point here is that most of the alternative methods had about the same short-term variability as a standard low flow. There was one exception to this. In the active no-purge method, where we saw higher short-term variability, both median and 90th percentile compared to the standard low flow. And the other point to emphasize here is that because data quality for the alternative and standard low flow methods were similar, there's no benefit to purging to parameter stability as compared to simply doing a fixed volume purge. And for each method, we also determined the cost of a 10-year monitoring program using that specific method at a hypothetical site for both a shallow and a deep well. We then combined these cost estimates with the results from our work to create the chart on the slide. Here on the y-axis shows increasing costs, while the x-axis shows increasing variability. So an ideal sampling method then would be both low cost and low variability and would be on the bottom left of the chart. And for our hypothetical site, we found that the alternative low flow small volume was the best. So for example, changing from the standard low flow to the alternative low flow small volume method could decrease total monitoring costs by almost 50%. It should be noted, though, that this cost analysis was done for one hypothetical site only, and that different sites should be evaluated on an individual basis to find the lowest cost option. So to summarize, our results showed that the alternative sampling methods did not change short-term data variability with the exception of the active no-purge method. And this is good news because sampling is usually done by different teams, and so data quality of the results won't be sensitive to specific procedures in the field. Next, because the standard and alternative low-flow methods had similar variability, there's no apparent benefit to monitoring purge parameters versus doing a fixed volume purge. In fact, it's simpler and in most cases takes much less time. And finally, because the sampling methods had similar data quality, the specific method that's best for your site can then be based on other factors like cost, ease of implementation, and sample volume requirements. And just as a quick side note, the data we obtained in our study was combined with data from 2 other field projects that also used the HydroSleeve. And all sites found that the HydroSleeve increased short-term variability, and we published these results in the manuscript shown here. Finally, we'd like to acknowledge our co-PIs on this project, Dr. Charles Newell and Sandy Britt. Thanks very much for everyone's attention. I'll now turn things over to my colleague, Dr. Tom McHugh, who'll discuss the second part of our project, which focused on analysis of monitoring data.
Great. Thanks a lot, Poonam. Okay, so I'm going to switch gears here a little bit, and we're going to talk about the second part of our project, where we looked at analyzing large monitoring data sets and trying to develop procedures that recognize that this short-term variability occurs and tries to find improved ways to analyze your data to identify long-term trends despite the fact that you have this short-term variability. And so for this part of the project, we were focused on 2 key questions. How much groundwater monitoring data do you need from a site in order to characterize the concentration trends, figure out how quickly things are cleaning up with a reasonable degree of confidence and accuracy? And then second, what's the trade-off between monitoring frequency and monitoring duration? What happens if you switch from quarterly monitoring to semi-annual monitoring or annual monitoring? And so the things we learned from this part of the project, we put into a tool for monitoring optimization that I'm going to talk about at the end of my presentation. So the first question we focused on was looking at how much data do you need from a site in order to have a reasonably good idea of what's going on. Are the concentrations decreasing over time? How quickly is the site cleaning up? And so to try and answer this question, we took large data sets from 20 different sites. Typically, a site had 10 years or more of monitoring data, and it was typically quarterly monitoring data. And we analyzed these large data sets to answer the question, well, how many years of quarterly monitoring data did you need before you could see statistically significant decrease in concentrations in 80% of your monitoring wells. And how much data did you need before you could estimate the attenuation rate with a reasonable accuracy that we defined as plus or minus 50%. And what we found was at the median site, at the typical site, you needed about 7 years of data to see this decreasing trend in 80% of your wells. And you needed about 7 years of data to estimate the attenuation rate plus or minus 50%. This was 7 years of quarterly monitoring data. These 20 sites, they were about half chlorinated solvent sites, TCPC, about half petroleum sites, BTEX, and then we had a couple of metal sites just to spice things up a little bit. But so we learned that it's sort of bad news. It takes a lot of data, on average or median about 7 years of data, before you can really understand the attenuation with a reasonable level of confidence. And so the lesson from this was that a lot of times people are making decisions about sites with less than 7 years of data. And there's a lot of uncertainty in these decisions. If you're using, say, 3 or 4 years of data to estimate the attenuation rate, the cleanup rate at your site, there's a lot of uncertainty in that estimated rate. You could be overestimating the attenuation rate or underestimating the attenuation rate. And either error can lead to erroneous decisions. So say you've been monitoring for 4 years, and you say, well, this site is just cleaning up really slowly, and you overestimated the cleanup time. You might say, well, I need to implement a more aggressive remedy in order to meet my cleanup time frame. Where if you had made that decision based on more data, a more accurate attenuation rate, maybe you would not need the more aggressive remedy. On the flip side, you might say, hey, this site's cleaning up really quickly. I'm going to be done in 20 years. And you set that as your cleanup goal. You tell all your friends, hey, we're going to be done with this site in 20 years. Another 5 years of monitoring data, you realize, well, it's going more slowly than I thought. Well, maybe 40 years would have been fine, but now everyone's focused on 20 years as the cleanup time frame, and maybe now there's more pressure to implement a more aggressive remedy because you originally underestimated the cleanup time frame. Okay, so that's how much monitoring data you need. And the second part, we looked at this trade-off between monitoring frequency and monitoring duration. Historically, groundwater monitoring has been focused largely on quarterly monitoring, and in the last few years there's been a lot of movement towards semi-annual monitoring or annual monitoring. And intuitively, you can see that if I collect 8 monitoring events over 2 years, I compare that to 8 monitoring events over 4 years. Well, the 8 monitoring events over 4 years tells me more about the attenuation at the site because I've had 4 years of attenuation instead of 2 years of attenuation. So just sort of from a common sense evaluation, 8 semi-annual monitoring events is more efficient than 8 quarterly monitoring events. But the question is, how much more efficient is that? And what's the penalty as far as the amount of time required to understand what's going on? And we tried to answer this question. We went to the mathematics behind the methods for estimating attenuation rates. So most people estimate attenuation rates using linear regression. And if you dive into the mathematics of linear regression, then you can quantify this trade-off between monitoring frequency and monitoring duration. And what we figured out was that that trade-off is the same at every site. So it doesn't matter if your site is cleaning up quickly or slowly. It doesn't matter if your site has a lot of short-term variability or not very much short-term variability. That trade-off between monitoring frequency and monitoring duration is the same. And so this slide advance has stopped for me. I'd like to be on slide 58 right now, if that's possible. Thank you. So this trade-off is the same at every site. Now, if a site's cleaning up really quickly, you can quantify the rates more quickly. But this trade-off between quarterly monitoring and semi-annual monitoring is the same at all sites. And that trade-off is 4 years of quarterly monitoring is always the same as 5 years of semi-annual monitoring or 7 years of annual monitoring. So the amount of information I learn about the site doing 16 quarterly events is the same as the amount I would learn by 10 semi-annual events or 7 annual events. And so if I switch from quarterly monitoring to semi-annual monitoring, the number of measurements I need to get the same amount of information is reduced by 37%. But the penalty for that in terms of time is that the amount of time I need to monitor increases by 25%, from 4 years to 5 years. Or if at my site I needed 8 years of quarterly monitoring to really understand what's going on, I would need 10 years of semi-annual monitoring. So again, it's a 25% time penalty. And so I don't have time to get into all the mathematics. It's pretty exciting math there, but we've documented that up in this paper that came out early last year, or late last year, in Groundwater. And that's an open source paper, so you can download it for free. It's great reading. Okay, so we took what we learned from this analysis of monitoring data and looking at short-term variability versus long-term trends, and we put it into this monitoring optimization and trend analysis toolkit. This toolkit has two basic sections to it. One is this trend analysis part. So if you have 5 years of historical monitoring data from your site and you load it into the tool will do a trend analysis. They'll give you the average attenuation rate across your plume and help you estimate when will this site meet groundwater cleanup goals. And a lot of tools do that, so that's not particularly novel. But what this tool adds on top of that is it does some analyses to tell you, are any of the individual wells attenuating more slowly or more quickly than the plume as a whole? And you know, if you use individual monitoring well data to estimate attenuation rates, if you look at 10 different wells at your site, you're going to get 10 different attenuation rates. And what this tool does is it tries to separate the random variability between those attenuation rates versus real differences across the plume. And so by looking at the overall magnitude of short-term variability at your site, it helps you answer the question for an individual well or a couple of wells close to each other. Does this well appear to be slow just due to random chance, random variability in my short-term monitoring data? Or does it really appear that this part of the plume is cleaning up more slowly than other parts of the plume? And by being able to separate that out, you can get a better feel for, in the next 5 years of data, is this well likely to sort of even out and catch up with the other wells? Or is this part of the plume cleaning up more slowly, and so if I need to clean up the whole thing within a certain time frame, do I need a targeted remedy for this part of the plume? So then the second part of the tool is this monitoring optimization part. And there, again, we take your historical monitoring data and we use the attenuation rate and the short-term variability to figure out for your site how much monitoring data do you need at this site to estimate the attenuation rate or the trend with a certain level of accuracy or confidence. And so if you have 3 years of data, it might say, well, you need another 3 years on top of that before you can really get the attenuation rate within plus or minus 50%. Or if you've got 10 years already, and the question you're asking now is, okay, I understand what's gone on for the last 10 years. I want to know going forward, have things slowed down? Is my remedy losing effectiveness? And it'll tell you, well, you need 6 years of additional monitoring before you can really be confident that your new attenuation rate is the same or different from your old attenuation rate. So it looks at that, and then it also looks at this trade-off between monitoring frequency and monitoring duration that I talked about previously. So it might tell you that 6 years of quarterly data will give you this answer, this reasonably accurate answer. But if you want to do it semi-annual, then it would take 7.5 years. Or if you want to do annual, it would take you 9 years to get the same level of confidence or accuracy. And then you can look at that trade-off between time and money. Is the cost savings that I get from less frequent monitoring acceptable or beneficial considering the amount of time that's needed to get the same level of answer? So just wrapping up this quick tour through our ESTCP project, we had 2 parts. We looked at groundwater sampling methods to see how does your groundwater sampling method affect the variability in your results. We find that for the most part, the groundwater sampling method doesn't change the quality of your monitoring data very much. So that tells us that when you're selecting a groundwater sampling method as a site, your primary focus should be cost and ease of implementation. That you really don't have to worry about, is this sampling method going to give me better or worse data quality? And specifically, we saw no benefit to monitoring purge parameters during part of the sample collection process. And that's one of the cost drivers for groundwater sampling. And so our results suggest you can save money by purging a fixed volume at low flow and not monitoring the purge parameters. The second part of our project was this monitoring optimization and trend analysis toolkit. We think it'll help site managers make better decisions by giving you a better understanding of attenuation rates and the uncertainty associated with those attenuation rates. It'll help you optimize your monitoring frequency by telling you how much data you need to understand an attenuation with a certain level of accuracy, and really clarifying that trade-off between monitoring frequency and how long it's going to take you to understand attenuation rates. With that, I'll wrap it up. We've got contact information, and I'll turn it over to our great moderator for Q&A.
Great. Thank you very much, Tom and Poonam. We do have a number of questions coming in, and again, I'd like to remind the audience you can submit your questions using that chat box. So the first question is about the first half of the presentation. Could you provide a definition of the low flow, low volume method and how you define that?
Sure. The low flow, low volume method was basically using a similar low flow strategy as the standard low flow that we typically use. But instead of purging to parameter stability, we purged to two different fixed volumes. One was a 3-liter, which was a small volume, and one was an 18-liter, which was the larger volume.
Okay, thank you. And what causes the main difference in cost between the two low flow methods?
Sure, that's a great question. We found that most of the cost driver was actually time in the field. So waiting for parameters to stabilize in the field using the standard low flow method usually took much longer than just purging simply to a 3-liter fixed volume.
Okay, and did you consider using passive diffusion bags in your comparison? Do you have information regarding them and short-term variability? And that's a question from the Washington State Department of Ecology.
Sure, I'll take that. We looked at, we considered the diffusion bags, and we considered them sort of functionally equivalent to the SNAP sampler. Both of them are sort of passive, no purge methods, in that the sampler just sits in the well, not moving for some period of time. And in the end, we went with the SNAP sampler because it covers a wider range of constituents. The ionic constituents that might not diffuse through a diffusion bag are captured by the SNAP sampler. But we, based on our conceptual model, the results for the SNAP sampler should apply equally to the diffusion sampler.
Okay, great, thanks. And did you identify reasons why the hydrous sleeve has more short-term availability?
We didn't really have a controlled experiment setting up to evaluate that. We took the data from this ESTCP project, and we also obtained data sets from a couple of other sites that we were not directly involved in. And based on that, while we had nothing definitive, we had some ideas. I think since we don't have a lot of time, the best recommendation is that people should look at that paper that was mentioned in the slide. That's an open source paper. They should read that, and that addresses some of those questions.
Okay. And when considering changing to the fixed low volume purge approach, what would determine that fixed volume?
We looked at 2 volumes, 3 liters and 18 liters. And 3 liters, if you have a 2-inch monitoring well with a 10-foot screen, the volume inside that screen interval is 6 liters. And so we just sort of arbitrarily chose half a screen volume and then 3 screen volumes as sort of being 2 fairly different fixed purge volumes. And we thought if we were going to see a difference with different purge volumes, it would stand out at sort of those two extremes, less than 1 screen interval and then 3 screen intervals. But we really didn't see much difference between that small volume of half a screen volume and the larger 3 screen volumes. And so our conclusion from that was that the fixed volume, the exact amount of the fixed volume is just really not that important.
Okay. And we have a couple of questions about purge parameters. One is, what's the regulatory acceptance of not collecting those purge parameters? And the second is, would you recommend collecting those parameters at some other point during the sampling, parameters like DO and ORP?
The regulatory acceptance question, it really varies a lot from state to state as far as what the requirements are, or for sites that are overseen directly by EPA, there's also some variation. So some guidance have specific requirements for low flow purge that require monitoring purge parameters. Others provide more flexibility. But what's acceptable for sampling has evolved a lot over time. We've gone from high volume purge to low flow to no purge is accepted in many states, but not everywhere. So the answer is it depends, and you really have to look at the guidance that's applicable for your site. As far as the benefits of monitoring purge parameters, in my experience, people collect a lot of data, and then there's not necessarily a specific use for it. So I would recommend people think about how are they going to use the data. So I wouldn't say definitively that it has no value, but just really think about how are you going to use it. How is it going to affect the decision making at your site? If you have a specific use for it, then collect it. If you don't have a specific use for it, then it's not worth the time to collect it.
And next we have a couple of questions, one of which is from the California Water Board, and it relates to how do the results of each of the two portions of your presentation vary between the constituents of concern being evaluated? So does it matter if it's the chlorinated solvents versus hydrocarbons or metals? And did you consider that question in your work?
It wasn't a primary focus. The main difference I've seen between chlorinated and petroleum sites, I think petroleum sites often have a little bit higher, faster attenuation rate. But in my experience, there's also a higher level of short-term variability. And often those two sort of cancel each other out, so that as far as monitoring requirements, you need about the same amount of data. As far as evaluating the sample methods, we evaluated the sample methods only at the chlorinated solvent sites. So our field study doesn't directly answer the question of whether we would see no difference in data quality at petroleum sites. But there's no obvious reason in my mind why we would expect a difference between them. But we haven't answered that directly with a field test.
Okay. How does matrix diffusion affect the estimates that you presented, Tom, for requirements for monitoring data?
Yeah, that's a good question. So our evaluation was built on this simple attenuation model of first-order decay, which is commonly applied for attenuation rates. Given the short-term variability that you see in most real monitoring data sets, if you use a more sophisticated model that accounts for matrix diffusion, usually even with 5 or 10 years of monitoring data, you don't see a better quality fit because there's so much noise in the data. And I think also that's sort of for predicting what's going to happen in the future, a first-order attenuation rate is pretty good for predicting the next 5 or 10 years, which, by that time, a lot of us will be retired, and so we don't have to worry about it. But certainly when you're looking at long time frames, about 50 years, 100 years, when you're looking at large concentration drops and asking, am I going to go from a high concentration today down to the cleanup standard, accounting for matrix diffusion is very important. And so whenever you're extrapolating concentration trends out a long way into the future, either a long time or a long concentration drop, that's where you should be really concerned that first order decay model is going to give you a lot of errors, and matrix diffusion models will be more accurate.
And we have a related question to what you were just discussing. How would your time versus cost evaluation change if you were just trying to positively identify a decreasing trend rather than getting an accurate attenuation rate? Is there a difference?
Yes, there is a little bit of a difference. But what we saw, we looked at sort of both of those. We looked at how much data do you need before you'll see a decrease in concentration trend that's statistically significant in 80% of your wells. And that for the average site, that was 7 years. And we also looked at how much data do you need to estimate the attenuation rate plus or minus 50%. And we saw that was also about 7 years. So on individual sites, you get a slightly different answer for those two questions, but on average, it's about the same amount of data.
Okay. And we'll have just 2 more questions for you, and then we'll bring Ron back. We have several questions related to the purge rate. Were the purge rates for the fixed volume purge and the standard low flow the same, and what were those rates?
Sure, I can take that one. The flow rates for the low flow standard were per guidance, so typically less than 250 milliliters per minute. And we varied them between purging and sampling. So when we sampled, we would decrease those flow rates. And then during the low flow alternative small volume purge, they were kept constant between purging and sampling, and were typically less than 1,000 milliliters per minute.
Okay, and the last question for you two. Where is the monitoring optimization and trend analysis toolkit available?
Yeah, that's been posted on the SERDP ESTCP website. So if you follow the link shown on the slide right now, that'll get you to it. I've also found that if you just Google the project number for any ESTCP project, it'll take you straight to that web page. So if you're not a very good typer like me, you can just Google the project number and you'll find the link very quickly.
Okay. Thank you very much, Tom and Poonam, for answering so many questions. We have many more, and if there's time, we'll come back and ask 1 or 2 more of those. Now we'll bring Ron back, and Ron, there were a couple of questions that came in that we'll now pose to just you.
Okay.
The first is, how do you determine how much mass is present to maintain the flux out of the low permeability zone over time?
Mathematically, I guess that means?
Yep, I think so. And I think the question might also get to how does that depend on the starting concentration, and is that considered?
Yeah, so the normal starting concentration would be 0 everywhere, and then the way I've been doing this is to simulate the contamination event and then the reversal of that. But one thing that I didn't mention is that the only thing that is stored from time step to time step is the mass that's in the low permeability zone associated with the Gridblock. So that's the only continuity really that's in the model. And then the P's and the Q's are recalculated at each step. But that mass is tracked, and you have to know it from the last time step to be able to have the mass balance be accurate for the next time step to close that mass balance.
Okay. And then the second question, we received a couple variations of this question, so I did want to ask you, Ron, have there been any studies that look at the concentration versus depth curve after repeated remediation attempts within the low permeability zone instead of only the natural diffusion processes?
Well, I know that that's a pretty active area of research, and I'm pretty sure that SERDP and ESTCP have ongoing projects or recently completed projects in that area. I can't name them specifically, but I'm confident that if you search through the recent and current projects, that you'll find a good bit of information in that area.
Okay. And Tom and Poonam, one more question specifically for you two. And again, this is an area where we've received a few different questions along these same lines. Did your studies addressing monitoring variability consider how much of the variability is due to just the natural variability in the groundwater system that's being monitored?
Yeah, that was the focus of a SERDP project that preceded this project. And there we looked at a number of factors. We looked at how the monitoring well is constructed, and we looked at the laboratory variability and then just the inherent variability in the aquifer. And we found that most of the variability in groundwater monitoring results appeared to be associated with just inherent variability in the groundwater system. And I think the results from this project support that finding because the sample collection method did relatively little to affect that variability. And so that's further evidence that it's just inherent in the system. And that's why I think the data analysis methods that account for that short-term variability are pretty important.
Okay. And one more question for you, Tom and Poonam. Other than what you presented in the first half of your talk, what other factors should be considered in the sample method selection? Are there other ones?
From what we've seen, I think that the cost and the implementability are really the key factors. At some sites, disposing of purge water is a really big hassle because they're remote sites without a lot of infrastructure. And in those sites, the no purge methods would be a lot more advantageous. Other sites, might have an on-site chemical wastewater treatment plant where disposing purge water is trivial, and it would be less of a factor there. Some specific analytes require larger volumes of water. And when you need those larger volumes of water, the no purge methods are at a disadvantage because they're limited in the total volume of water that they can collect. And so their purge methods would be favored. So I think it's really the cost and implementability considerations are the key factors.
Okay, thank you. And now I would like to ask a couple of general questions to all of our presenters from today. The first question is about what role do you think screening level models play in site remediation design, such as the models that we talked about here today. And we'll start with Ron, and then if Poonam and Tom, if you would like to also address the question, we can follow Ron.
Well, I would say that these should be used at an early stage prior to the development of a comprehensive three-dimensional numerical model, just to kind of see the order of magnitude of the system response to propose different activities, and just to kind of get your arms around the problem before going into more detailed modeling.
Okay. Tom, Poonam, do you have any input on what role screening levels would play in site remediation design, or the toolkit, for example? Could that be applied at all to site remediation?
Yeah, I probably don't have a lot to add, but I think screening models can be very useful for giving you an understanding of what factors could be important at your site. For example, answering the question, is matrix diffusion likely to be really important at my site or not so important? And evaluating that with a screening model first, and then moving to a more sophisticated model that does focus on that or maybe doesn't focus on that can be very helpful.
Okay, thanks, Tom. The next question we'll start with you, Tom, and Poonam, and then move to Ron. What do you envision as the next steps after completion of these projects, or just the next steps in general with respect to these topic areas in terms of research and also moving them into the field more broadly?
Sure, that's a great question. I think the next step is maybe disseminating that information. So we've published the results of our field program, for instance, and 2 other manuscripts related to the toolkit, which should help disseminate the information, and also created training materials that we're ready to discuss at any training workshops in the future. Anything you'd like to add, Tom?
Yeah, I think as far as groundwater monitoring, sort of maybe the future of groundwater monitoring. So the question about is the variability inherent in the system, and I think a lot of that variability just sort of is baked in. And so one sort of long-term approach would be to figure out ways to collect time-integrated samples. In groundwater monitoring, it's always grab samples, whereas in a lot of other monitoring that we do today, we take more longer-term samples. In air, we commonly take 1-day or 7-day samples. In sediments, there's been a movement towards taking long-term time-integrated samples. And I think that taking time-integrated samples in groundwater might be the best way to address some of that variability.
Okay, thank you. And Ron, what do you envision as the next step for your work?
Well, I think, following the finalization of this, the most important thing would be to try to apply it to real sites and learn better how to measure the key parameters for this kind of a model. For the simpler case of just an aquifer and Aquitard, we know that geometry, but for the more general case of a fractured system or one with heterogeneities, we need to be able to relate easy to make measurements with what needs to go into the model. So I see that as the big goal.
Okay, thank you. And with that, I would like to thank all of our excellent speakers today, and thank you all for answering the audience's questions as well. And for the SERDP ESTCP webinar series, I'd like to let the audience know that our next webinar is on Thursday, May 5th. It will feature 2 presentations on microgrid solutions for increased energy security. And the presenters will be Dr. John Salsel from Bosch and Ryan Ferries from Raytheon. And registration is open for this webinar. And if you're interested in this or any future webinars, please do visit the SERDP ESTCP webpage to register. Before we conclude, I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. And we would appreciate it if you could please take a moment to complete the survey that will pop up on your screen at this time. And this concludes today's webcast. Thank you.